Yeah, welcome everyone to the third lecture of Curry Leaf by Professor Diganta Borah from ISER Pune. And yeah, over to you. Please start.
Yeah, thank you, Sam. Let me share the screen first.
Yeah.
It's visible, right? The screen?
Yes, we can see. Yeah. Please.
Okay, great. So, okay, so last time we started discussing the Dirichlet problem. So on a disk, we know how to solve the Dirichlet problem. We simply look at the Poisson integral of the boundary data. That gives you a solution. And we also discuss a few properties of harmonic functions, such as the maximum principle, mean value theorem, right? So today we'll see one more consequence of this Poisson integral formula. So this is the so-called Harduk's theorem. But before that, I want to recall or like make an observation. This is based on an exercise that I gave last time. So this exercise, let me first recall this exercise. This is basically the Harduk's inequality. So if H is harmonic on some disk, then the Harduk's inequality basically says that you can control the function by its values at the center of the disk. So it looks like the following. So you have some VI draw a picture here. This is R. So you take any point inside the disk. Say that. So this is going. So Z is this is going to be of the form Z naught plus some R e power I theta. So the inequality is, so the value at so you look at R minus R by R plus R, U at, sorry, not U, H at Z naught. This is equal to H at this point Z. So Z naught plus R e power I theta. And this is bounded above by R plus R divided to H at Z naught. It's easy to derive this inequality. So S is a positive, sorry. Yeah, it's an important. S is a non-negative actually, but usually non-negative harmonic functions are in the literature called positive harmonic. Positive. This means greater or equal to 0, positive. So basically non-negative. This is an important point, okay? Otherwise you don't have this. So if H is a positive harmonic function on disk, it has this property. So here actually you basically look at the Poisson integral formula for H. Possibly you have to work first on a smaller disk because to apply the Poisson integral formula, we need to know that the function is continuous up to boundary. So you first work on a smaller disk, look at the Poisson integral formula, and basically show that the Poisson kernel would be, can be bounded above and below by this quantities on the smaller disk. So R will be replaced by the radius of the smaller disk. And you apply a limiting formula to obtain this. This is easy to achieve, so let me not go into that. Now, so what is good about this? See, these numbers, these two numbers, they do not depend on the function H. So this is so the same numbers work for any positive harmonic function on this disk. So in particular, so let's now see how this what does it give if we apply this to a sequence of harmonic functions. So let Hn be a sequence of positive harmonic functions. So this inequality now is true for H. You can take H to be Hn, and thus inequality is still true. So let's write it down even. So then we have R minus R, R plus R, Hn at Z naught is less equal to Hz Z naught plus R e power I theta. This is less equal to H n at Z naught. This is H. Okay, so you can immediately see the following. Suppose you know that this, so let's write it down. Suppose Hn at Z naught converges to plus infinity. Then if you look at the first part of this inequality, so you look at this part. So at any other point Z, because it is less equal to, so the value at Hn at Z is greater or equal to some constant times Hn at Z naught. So this would immediately imply that Hn at Z also goes to infinity. Right? So then Hn at Z also converges to plus infinity for all Z in this disk. So in other words, if a sequence of positive harmonic functions converges to plus infinity at some point, it converges to plus infinity in the neighborhood of this point. This is what this thing. You can actually say something more. Here you see this bounds, these numbers, R minus R divided by R plus R. They do depend on, they don't depend on the functions, but they do depend on the argument Z, right? So Z has this Z naught plus R e power I theta. So these numbers do depend on R. But you can get rid of this by working on a smaller subdisk. So if you look at, say, for example, here, let me draw another picture. So now suppose I allow, this is my original disk, Z naught, radius R. So suppose I allow Z to vary on a smaller subdisk, something like this. So radius rho. So I will be taking Z from here. So Z is here, Z equal to Z naught plus R e power I theta. But R is less than or equal to rho now, right? So this allows you to find uniform bounds for this. So what do we have now? So let me rewrite this this inequality here, the left inequality. Yeah, because rho is now R is smaller than rho. So what you have is R minus rho, that will be smaller than R minus R. Okay? Rho is bigger than R. Sorry, rho is R is smaller than rho. So this is going to be, in fact, let me write like this. So this is Sn at Z naught. This is less equal to R minus R divided by, and then you already have Hn at Z naught plus R e power I theta. Yeah, so the good thing is that now if you look at this guy, so you see this number R minus rho R plus rho. That is this doesn't depend on Z. So in other words, what you can say now is that if Hn of Z net goes to infinity, so Hn of Z will go to infinity uniformly, as long as Z lies in this blue disk. Okay, so let me write that down. Moreover, if so rho is a number less than R, so then Hn of Z goes to plus infinity uniformly, on this disk. You can take the closed disk, in fact. Okay, so if you take a smaller subdisk, so there you have in fact uniform estimate. The same is true. So now suppose you have the sequence Hn of Z naught. So suppose you know that Hn of Z naught is bounded. Okay, so this is another. So now I'll be looking at this part of the inequality. Okay, so if I know that Hn of Z naught is bounded, so right hand side is bounded. So you can immediately say that Hn of Z is also bounded, right, for all Z. So if Hn of Z naught is bounded, then you can say that Hn of Z is also bounded. So I should write maybe like, so this is for a fixed point. So the sequence is bounded. That's what I have. So this will also be bounded for each Z in Bz dot R. Again, if you walk on a smaller subdisk, you have an uniform bound actually. So also on the Z naught comma rho bar, it is uniformly bounded. So this observation basically is saying that if you have a sequence of positive harmonic function, and if it converges at some point, so converges to infinity at some point, then it will converge uniformly in the neighborhood of that point. And if it is bounded at some point, then it will be uniformly bounded in the neighborhood of that point. We'll also talk about some convergence property. That's what is the Harnack's theorem, which I'm going to discuss now. Okay, so let me write down the Harnack's theorem. Okay, so it says that, so let say H1 is equal to H2 is equal to H3 is equal to so on, be an increasing sequence of harmonic functions. I'm not assuming that they are non-negative, just an increasing sequence of harmonic functions. Then on a domain D. So let me underline this. This connectedness will be used is necessary for the statement that I'm going to do. So this is harmonic on D. Then either even converges to plus infinity uniformly on compact subsets of D, or Qn converges uniformly to a harmonic function on compact subsets. So the limit is so the limit exists. It says that it is it could be it is either identically infinity or it is a harmonic function. Okay, and the convergence in the case of finite limit, it is actually the convergence is also uniform on compacts. The limit is harmonic. Okay. The proof is now not very difficult once we keep the observation in mind. Okay, so here how it goes. So see, first of all, without loss of generality, we assume that this H1 is greater or equal to 0. Okay, in other words, all the members are now positive. So this is we can do this because you see, what I can do, because I can actually consider if not, I can consider otherwise. So so you consider the new sequence. This is Hn minus H1. Because it is an increasing sequence, the given Hn, so this is always non-negative. And you establish the theorem for this sequence. But then you can recover the original sequence by simply adding H1 to the sequence Vn. So there is no loss of generality if you assume that all the members are all negative. Okay. Now, let's do the following. So let's define a new function. Let u of z. Maybe I'll write h. Let h of z. This is the supremum of set of z. This supremum could be infinity. Okay, we don't worry about that. It could we allow plus infinity also. But what you should notice is that because the given sequence is increasing, so this supremum is actually the limit, right? So then h of z is actually the limit of hn of z. This is as hn is increasing. All right. We don't know whether hz is finite, infinite, but we are going to take care of this. We are going to consider both the situation. So so let's define some sets. So let A be the following set. A with the set of all z in D, such that this Hz, this supremum is actually plus infinity. Okay, and let B be the complement of A. That means this is the set of all points where Hz is finite. Okay, so B is the complement of A. So definitely you have basic. So this B is definitely A union B, right? This is clear. Something more we can say about these two sets from our observation. Recall the observation says that if I know that a sequence is sequence of positive harmonic functions converges to infinity at some point, it will converge to infinity in a neighborhood of that point, right? So this means that if you take a member in A, then there is a disk sitting inside A, right? So A is an open set. So by our observation, A, and in fact B also, you see, we also saw that if the sequence is bounded at some point. Now Hz being finite means because H is the supremum, right? If H is finite, so this sequence is bounded basically. So if the sequence is bounded at some point, our observation says that it is bounded in a neighborhood of that point. So if something is in B, a neighborhood of that point is also in B. So this means our observation, A and B are open. So this is a partition of the set B. But remember, D is connected. So therefore, either D is A or D is B. These are the only two possibilities. Either D is A or D is B. So let's explore each of these cases separately. So case one. So let's see what happens when D is equal to A. So this means that Hz is infinity for all Z in D, right? So the sequence converges to infinity at every point. But we just saw that if it converges to infinity at some point, the convergence is actually uniform. It converges uniformly in the neighborhood of that point. So if you take any compact set, we can always cover it by finitely many such neighborhoods. So this, by our observation, So Hn converges to plus infinity uniformly on compact subsets of D. Okay, so this case is done. So this is one possibility. The second possibility, so we have to show that if there is one point where it doesn't converge to plus infinity, then it has to converge uniformly to some harmonic function on compact set. Okay. So here D is equal to B. So how do we do this? What we have seen in the observation is that if the sequence is bounded at some point, it is uniformly bounded in a neighborhood of that. But here we have to discuss convergence, right? We have to see convergence, but that's not kind of difficult. So recall. So by our observation, so question. So let's suppose you have some disk, some centered at Z0. Well, actually, I'll consider a disk like this. I will consider a subdisk of a disk inside D. Okay, closed subdisk of a disk inside, because I want some uniform estimate, and this is in D. So I'm taking. So let's look at the following this picture here. So I'm in this situation. Okay, so I have a smaller subdisk of radius rho inside a subdisk of radius r, which is inside D. So here I have this this estimate, right? So let's look at yeah. So I want to look at this estimate here, and in fact the uniform estimates that that we have on the smaller subdisk. So let's write it down. So the Hardox thing says that then for any harmonic function on D, so we'll be able to write so I need only the one part, the right part, that says that so the U is U at you have something like this, U at Z0 plus R e power I theta. This is less equal to. So initially you have this U at Z0. But if you allow Z to vary, so this is Z0, so Z to vary in the smaller subdisk, this is like bounded by this uniform bond, right? This is true for Z equal to Z0 in this disk of radius rho. You can take closer. So this is true for any positive harmonic function. So now you see Hn is increasing. I also assume that all of them are non-negative. But what about so you apply this to the following function, Hn minus taking U to be Hn minus Hm. So I want a non-negativity, so I'll take for n greater or equal to n. So you look at this guy. So this is definitely difference of harmonic functions. So harmonic. It is also non-negative because Sn is increasing, right? So n is greater or equal to m. So apply this inequality to this function. So you immediately have Hn at Z minus so Hn minus Hm at Z. This is less equal to R plus rho divided by R minus rho. So you have Hn minus Hm at Z0. Now the things are very clear. If at some point the sequence converges, the sequence is in fact you are in the case where at every point the sequence converges, right? You are assuming that supremum of this increasing sequence is finite. So which is the limit. So if this sequence converges at every point, so for example, at converging at Z0, then you look at this. So on a subdisk of radius rho inside this bigger disk, you basically have uniform convergence because it is uniformly Cauchy, right? So Hn by Hn is uniformly Cauchy in disk, and hence converges uniformly. But now, given any compact set, I can always cover it by such finitely many such disk, right? So thus Hn converges uniformly on any compact subset of. Well, the limit you already know to which is H. And we also saw last time that if you have uniform convergence, locally uniform convergence of harmonic function, limit is always turns out to be harmonic. Right? The mean value property holds for the limit, and hence it has to be harmonic. And so H is harmonic. So this completes the proof of the Harnack's theorem. Okay, for positive harmonic functions, either you have the limit is identically infinity, or it converges uniformly to some harmonic function. Okay, so these are all the properties that we need to take the Dirichlet problem. So now we'll move into a method for solving this problem. So the method that I want to discuss is known as Perron's method. Okay. So the Perron's idea is to, if you recall, the Dirichlet problem is basically to find a harmonic function on a domain D with prescribed boundary values, right? So Perron's idea is to first consider sub-solutions to this problem. Okay, and look at the upper envelope of this sub-solution to get an idea what they are. So let's actually consider this in the case n is equal to 1. Okay, so some motivation. So let's try to understand the situation in n is equal to 1. So here you see the analog of the Laplacian is basically d2x d square dx square. There is only one variable. So the analog of the Laplacian will be d2 dx square. So, but then what are the harmonic functions? Harmonic functions now are, so for example, so you take an interval. Okay, so the domain we want to consider, right? Open connected set. So let's take an interval, open interval. So a harmonic function means its second derivative is 0. That means the function has to be linear, right? Linear polynomial. So affine maps, right? So this means harmonic functions on an interval, open interval, are precisely the linear functions, linear polynomials. So linear, when I say linear functions in analysis, we allow the constant. Okay, not like in linear algebra, you have to 0 has to go to 0, but usually here it basically means the affine maps in terms of linear algebra. So now what would be the Dirichlet problem now? So if you have something like this, so this is an so let's consider an interval, some a to b, and you want to find a harmonic function, so it boundary values given, right? So at a some value is given, and at b some value is also prescribed. So you want to find a harmonic function with this boundary values, but as we have noticed, that function has to be linear. So its graph is going to be like segment joining these two points. right? So the solution is a line segment joining these two. Then one way to obtain this line segment is to consider the following. So let's look at all the graphs below this line segment. Something like this. So let's take, nice, just differentiable maybe, or maybe smooth. So graphs, you look at all the graphs below this, and you realize what kind of functions they are, right? They are basically convex functions. So you look at the convex functions with the same boundary values. And you look at the upper envelope of this yellow family, which means that you given a point x here, you look at the supremum here. So that supremum will converge to point on the line segment, right? So this is one way to achieve this, and this was the Perron's idea. So you basically, so I'm going to talk about, so these yellow things are kind of, you should think of as sub solutions. They have the same boundary values, but they lie kind of below the harmonic functions, which is linear here, right? So convex functions are kind of sub solutions to these harmonic functions. So this was Perron's idea. You find the sub solutions and try to, look at the upper envelope of this, and possibly that will give you a solution. So first, we need to understand this concept of sub solutions in higher dimensions. So this convex function, basically the analog of the convex functions, and they are called subharmonic functions. So first, we'll recall or rather study these functions, some properties of these functions, the subharmonic functions. They are analog of this one variable convex functions. We will see why. So let me first give you a definition. So let you from, so I'll take a, let D be a domain. In C, and U from D2, I am now going to allow, extended real numbers to the values of U, only minus infinity. I'll allow U to be a function from D to minus infinity, and be a continuous function. So it gives a certain flexibility. Okay? Now, continuous, you see, you are allowing extended real values also. So if at some point the function takes the value minus infinity, continuity at that point means the limit as z goes to that point, the limit should go to minus infinity. Continuous function. So in general, subharmonic functions are defined for upper semi-continuous functions, but we will actually work with continuous functions, for convenience, basically, nothing more than that. Be a continuous function. We say that U is subharmonic if, we call harmonic functions are those functions which have mean value properties, right? So we define subharmonic functions as those functions which have sub mean value property. What does it mean? If for so let's draw a picture. So this is your domain D, say, and what I want is that given any point, I can find some epsilon such that, so we already have seen this thing for harmonic function, such that for any disk of radius smaller than that epsilon, So there is some disk actually you can find. First of all, some epsilon disk. So this is some epsilon, and inside you take any disk, then you have we did right on the previous disk. If for each z naught in D, there exists epsilon greater than 0. This can depend on z naught. Point to point, it can vary. Exists epsilon greater than 0, such that u at z naught is less equal to 1 upon 2 pi. So for mean value equality, you have equality. Mean value inequality or sub mean value property, you have basically less equal to 0 to 2 pi u at z naught plus r dt. See, although some values could be minus infinity, you don't have to worry too much about this integral. Integral, of course, we define as you look at the positive part and negative part. So integral of u will be integral of u plus minus integral of u minus. But you can actually make the following observation. You see, if u z naught at some point it is actually minus infinity, then this inequality is always is trivial, right? So remark. So this, let's write as a remark. If u z naught is equal to minus infinity, the inequality trivially holds, evidently holds. Left side is minus infinity, so you don't have to worry about the other things. And if u at z naught is finite, then because of continuity, you will be finite in the neighborhood of z, right? And so this integral, basically you want to integrate a continuous function on some circle. So this is not a big deal, right? So this is fine. So, right. So let's see some examples. Well, first example you should observe is that any harmonic function is always subharmonic, because you have then mean value equality, right? So you have you definitely have sub mean value property. So any harmonic function is subharmonic. In fact, you see, if H is harmonic, its negative is also harmonic, right? So it's subharmonic. So harmonic function, and also if you have a function which is both subharmonic and its negative is also subharmonic, then this inequality becomes equality. So harmonic functions are precisely those functions which are subharmonic, as well as their negative also subharmonic. Okay, so both h and minus h subharmonic would imply h is harmonic. So the second example. So look at the function log mod z. Maybe u z is equal to log mod z. This function is subharmonic on all of C. This is because you see, okay, first look at the point z equal to 0. The function is minus infinity there. Log 0 is minus infinity there, right? So there, but we know that the inequality trivially holds. So you don't have to check the mean value inequality at z naught, at 0, right? It trivially holds. So at z equal to 0, this mean value or sub mean value property holds. Let's sub mean value property holds. What about away from 0? But away from 0, this function log mod z is this is the real part of log z, right? So this is a harmonic function. So the sub-mean value property definitely holds. So on C minus 0, U is harmonic. And so there also sub-mean value property. So this proves that log mod Z is subharmonic in all of C. You can do a little more work to actually show that. So this I leave as an exercise. If F is a holomorphic function on D, then log mod F is subharmonic. You can use the previous example to show this. You have to observe certain that it is certain composition of certain functions. So, but I leave is an exercise for you. All right, good. So these are subharmonic functions. So at this stage, as I said, they are analog of convex functions. So here is an exercise for you. One more exercise. So this I will not go into because of we have limited time. Okay, but nevertheless, it's an easy exercise to see. So if U is a C2 smooth, so twice continuously differentiable function on D, then you can show that U is subharmonic if and only the Laplacian of U. This makes sense now, right? Because I am assuming U is C2 smooth, so this is always greater or equal to 0. The second derivative is negative, so something that's why I say it's an analog of convex function. Okay? This can be checked using the Green's formula. So I again leave it as an exercise. So this shows that subharmonic functions are analog of convex functions, real one variable convex functions. Okay, we'll need certain properties of these functions to talk about the Perron's method. Properties similar to those of harmonic functions. So let me write down some of them. Okay, so first few observations. So let U comma V be subharmonic on D. Then first of all, observe that sum is also subharmonic. This is immediate from the definition because both U and V satisfy the sub-mean value property, right? U at Z0 is less equal to something, V at Z0 is less equal to something, and an integral is linear, right? So U plus V at Z0 will also satisfy the sub-mean value. So it is immediate from the definition. You multiply a subharmonic function by a positive number, you get a subharmonic function. That is again immediate from the sub-mean value property. You can take the constant inside the integral. So not at all. But note that you cannot multiply by a negative number because the inequality will reverse. So only positive multiplication is allowed. And here is another observation. If you have two subharmonic functions, the maximum is also subharmonic. This is also not difficult to see. First of all, this maximum of two continuous function is continuous, and then you have to see that the sub-mean value property holds. But again, you see both U and V has this sub-mean value property, right? So let's at least this one, let me write it down. Okay, so you have this sub-invalid property. So u at z naught is less equal to 1 by 2 pi. You are working on some epsilon and all these things you have already fixed. So you choose an epsilon which works for both u and v. Okay, so you take the smaller one. First you find an epsilon for u and an epsilon prime for v, and then you take the smaller one so that we have a common epsilon. So you have done this thing. So you add z naught plus r to power theta, and you have v of z naught. This is this equal to, we have this. Okay. We want to go to the maximum. So first you walk on the right hand side. So here it is, see, I can replace u by the maximum, right? The inequality will remain true. So you replace by a bigger function, maximum of u and v, and then at z naught plus r e power I theta d theta. Same is here. 0 to 2 pi. You replace, so v is smaller than the maximum. So u comma v at z naught plus r e power I theta d theta. But then now on the right hand side we have an uniform number. So this implies that the left hand side is also, so maximum of u comma v at z naught also less equal to the same number, right? 1 upon 2 pi v at z naught plus r e power I theta d theta. So this takes care of the sub-invalid property for the maximum. Can try with minimum, but minimum is actually it doesn't turn out to be subharmonic. We can see some counter examples, maybe some exercise. Okay, some more interesting properties. The first one is, like harmonic functions, subharmonic functions also satisfy maximum principle. So what it says is, so let D be a domain, and yes, so let U be a subharmonic function on a domain D, right? If U attains maximum at some points a at some point D, then U is constant. Same as harmonic functions, right? If it attains maximum somewhere inside, then the function has to be constant. And the proof is exactly same as for harmonic function. That's why I say I'll write down the proof for harmonic function, because the exactly same proof will work here. So I just briefly write what you need to do, because everything is same, except you have now mean value inequality. So you basically look at all points where the maximum is there. Okay, so look at the set. So let A to be the set Z in D, such that, so first to look at the maximum to be at the, so let suppose you attains maximum at Z naught in, then consider the following set. Let A to be the set of Z in D such that U of Z is equal to this maximum. Okay. And as in the case of harmonic function, show that so A is of course not empty. Then A is not empty. Show that A is what? Open and closed. It's already closed, but you just need to show that it is open. Okay. So and this argument is exactly similar to the harmonic function. So I don't repeat them. But then since D is connected, A is all of D, and that proves that the function is constant. Okay. So yeah, it's the same arguments as for harmonic functions. So I want to write down one more version that actually follows from here. So this version says that, so let U be a subharmonic function on a domain D, and suppose that look at the lim sup of U as Z goes to zeta, which is the boundary point. This is less equal to some constant, say M. This is true for all zeta in D. Then you can say that U is less equal to M in D. So on the boundary, so lim sup is supreme of all possible limits, right? So if you know that lim sup is bounded by this constant M on the boundary, then the function is dominated by the same constant inside also. So this is again analog of one version of maximum principle that we saw for harmonic function. So this you can achieve from the first one, the first version, by simply considering the following. So proof. Actually, you see, I can assume this M to be 0 here in the proof, because otherwise I have to look at the function simply U minus M. U minus M is again subharmonic, right? If U is subharmonic, this is constant will, because constant is harmonic. So minus M will also be subharmonic. So U minus M will be subharmonic. So that is less equal to 0 on the boundary now, lim sup. And you show that U minus M is less equal to 0 inside. And then that will give you U less equal to M. So enough to assume that it is without loss of generality, we can assume that M to be 0. So without loss of generality, so take M to be 0. Okay. Now you consider the following function. So consider, so look at V to be maximum of UN 0. Actually, you don't have to take M to be 0. You can, otherwise you can take the maximum of UN M, the same proof will go. Okay. But anyway, so let's, for simplicity, let's take M to be 0 and look at this function, the maximum of UN 0. So we have seen that maximum of two subharmonic function is subharmonic, right? So this is subharmonic. On the, what is happening on the boundary? Well, For u, I know that. So let's see some part of the boundary, say zeta. So as z goes to zeta, all so look at limit of u, limit so lim sup of u. Okay, so supremum of all possible limit that is less equal to 0. It cannot be more. So whatever all limits of u actually at zeta are less than or equal to 0. Whereas you look at this part. So this I am looking at v to be maximum of 0 and this. Okay, so this part is going to 0, and u part is less equal to 0. So the maximum will actually go to 0. The limit itself will exist and go to 0. So note limit z going to zeta, we observe this limit will exist because it is the maximum of un 0 and u, all possible limits of u are less equal to 0. So that part will go to 0. So this will give you to 0. So what does it mean now? V is a V is continuous up to D, right? Continuous on D bar now. V is subharmonic when it is continuous on D bar. And so subharmonic on D, right? V is continuous on D bar, subharmonic on D. So because of continuity on D bar, so I should have taken D to be a bounded domain here. Okay, so let me see. So I'll take it's a bounded domain. Sorry. Now continuity of V on this D bar, which is a compact set, implies that V has some maximum somewhere. So V, suppose V attains maximum at some point, said not in. This is not suppose. V attains this. V attains maximum at some point z not in D bar. Okay, let's try to understand what could be the value of this maximum. I don't know whether it is on the boundary or this. So let's try to consider both the cases. So I want to evaluate what is. So we want to compute this thing V at z naught. Let us try to find out this maximum value. So two cases we have to consider. So if z naught is in D, then the subharmonic function is attaining its maximum in the interior, right? Then V has to be constant. Then V is constant. But then this constant value has to agree the boundary value of V, which is 0, right? So this constant, so V is actually constant. This constant must be equal to 0 because 0 are boundary values, right? So therefore, in this case, the maximum is 0. What about if this point is on the boundary? If z naught is in delta D, well, the function, look at the function V. So V boundary value of V are 0, right? If z naught is in delta D, then V, of course, z naught is 0. So what we have seen is that the maximum of V is always 0. So thus, V at z naught, both the cases, the maximum of V is 0. This means that V is less equal to 0. But recall, V was the maximum of U and 0. U is no more than V. So this definitely U is also less equal to 0. This is what I wanted to prove, right? U is always less equal to 0. Okay. Right. So if a subharmonic function, if its lim sup is bounded by some constant on the boundary of a bounded domain, the function has to be bounded by the same constant. So here's a corollary of this. So let D be a bounded domain. U is subharmonic function D. Function on D, and V a harmonic function on D. On D, and assume that they are continuous or continuous up to boundary on say D bar, and assume that U is less equal to V on the boundary. So you have a harmonic function that dominates a subharmonic function on the boundary. Then, well, you look at the function U minus V. U minus V will also be subharmonic function, right? Because V is harmonic minus V is subharmonic, sum of subharmonic is harmonic. So U minus V will be a subharmonic function. And on the boundary, what is happening? It is less equal to 0. I'm assuming that both the functions are continuous up to the boundary. Okay, so U minus V is a subharmonic function, which will be less equal to 0 on the boundary, and hence it has to be, by the previous result, it has to be less equal to 0 inside also. So that means U is less equal to V in D. So this result is saying that if a harmonic function dominates a subharmonic function on the boundary, then it dominates everywhere. It's like, the one variable analog that we have seen. We have linear function, okay, and you have a convex function with the same boundary value. Then the convex function will lie below the graph of the linear function. This is exactly the analog of that statement for higher dimensions. Okay, this is a very important consequence. So I am now, ready to start discussing the Perron's method. So maybe here I will take a few minutes break. Maybe we need to take a break, right? 5 minutes break I'll take here.
Yeah. Okay.
Right. Okay. Shall I begin?
Yes, please.
Okay, so this version of the maximum principle says that if a harmonic function dominates a subharmonic function on the boundary, then it dominates everywhere. So in some sense, so harmonic functions are above the subharmonic functions with same boundary values. Like in the one variable analysis, we saw that the line segment lies above the convex functions, right? The graph of convex functions. So this allows us to, so here is so let's revisit this. So Perron's method. So what I'll do, so let D be a bounded domain, and f from say delta D to R be a continuous function. Okay. So the Dirichlet problem is to find a harmonic function in D which is continuous up to the boundary with boundary values f. Now suppose the solution exists. Okay, suppose let's call H is a solution to the Dirichlet problem. Of course, it will be unique once it exists. So let's assume that it exists. Okay, Dirichlet problem with boundary data. Yeah. So you have some domain, bounded domain. So say D, and so some function is prescribed on the boundary. F is given on the boundary, and you want to find. So there is a harmonic function H inside. This is continuous up to the boundary and equals to, so delta H is 0 and H is continuous on D bar and H is equal to F on delta D. So this solves the Dirichlet problem. And now, suppose I have any subharmonic function with the same boundary value F. So let's suppose U is a subharmonic function on D with, and let's assume that lim sup of U of Z going to D, zeta, this is less equal to F zeta. This is true for all zeta in boundary. So you are taking a subharmonic functions with whose boundary values in lim sup sense, okay, is not more than F. Well, we have a harmonic function with boundary values F. This means that this U, so by the way, this U, let me give it a name. So we'll call we will call such an U a subsolution. It's a subharmonic function and boundary value is not more than the given data. So we'll call it a subsolution. And also, so let's we'll denote the family of all subsolutions by this curly P, and call it the Perron family. Perron family corresponding to the boundary data F on delta. Okay. So I am looking at a subsolution. Now you see H is a harmonic function with boundary value F. U is a subharmonic function whose boundary value not more than F. So U is less equal to V on the U is less equal to H on the boundary, right? So this so the previous corollary implies that then U is less equal to H in D. So any subsolution is not more than the solution to the Dirichlet problem. So always less equal to it. But you see, H itself is a subsolution, right? Because it's a harmonic function. And so it is subharmonic and boundary values are F because you are assuming it is the solution. So H is also a subsolution. So moreover, H is also a subsolution. So all subsolutions are dominated by H. H itself is a subsolution. So that therefore, H is nothing but the supremum of these subsolutions, right? H at Z is equal to supremum of U at Z. So U is coming from this Perron family. Right? So it is the upper envelope of subsolutions. So if a solution exists, this observation shows that it has to be the upper envelope of subsolution. So if a solution exists, it has to be the upper envelope, by which I mean this supremum, okay? Upper envelope of the subsolutions. Okay, so if a solution exists, it has to be the upper envelope of subsolutions. So Perron's idea is to kind of walk it backward. So now you look at, so if you have a boundary data, try to look at the subsolutions and then look at the upper envelope, because you know that if solution exists, upper envelope has to be the solution. So you look at the upper envelope and try to show that, or try to check rather, because we don't know whether it provides us a solution. Okay, so that is what the Perron method is. So I'll write down as a theorem. And it turns out that most of the cases, it is actually some boundary, condition is required, but we'll discuss that. So theorem. So let D be a bounded domain. And F from delta D to R to be a continuous function. So so let's look at the upper envelope. Let's denote it by F tilde. So this is defined as supremum of U Z such that U is in the parent family. Okay. So here when you talk, so now see earlier I assumed that there is a solution and the parent family is actually non-empty. But here I have to actually first understand that the parent family is non-empty to talk about this theorem. But nevertheless, I'll do that. Okay, so but assuming that suppose F tilde is defined as the upper envelope. So this is called F tilde, we call F tilde the Perron solution. So the theorem says that F tilde is always harmonic, is a harmonic function. Only. So it says that the parent solution, this upper envelope of so you start with some boundary data. We do not know solution exists or not. We are trying to see this. Okay. So you look at the sub solutions and you look at the upper envelope. This theorem is saying that the upper envelope is always this parent solution is always a harmonic function. But what can go wrong is that this harmonic function, may not take the boundary values. That is the only things that can go wrong, because it is always harmonic. That's the very interesting part. So no matter if you start with any continuous function and without any boundary condition, any boundary regularity of the parent solution that you have is always a harmonic function. Of course, then later on we'll show that with some boundary regularity condition, it actually takes the boundary data. So you need to first understand that this for the statement to so this F tilde to be well defined. So you need to know that this family is non-empty, but that's not difficult to see. You see, the boundary function F is continuous, right? Delta D is compact, so it is bounded. So let M is maximum of mod F on delta D. All right. Then so this is minus M is less equal to F is less equal to M. So but then this minus F, this is a constant function, so it is a subharmonic function, and if it is less equal to F on the boundary, it has to be the Perron family, right? So this is in PF. So this family is always non-empty. Okay, so this statement is well defined. All right. So to prove this, first we need to make few observations here. So I'll write it as a lemma. So these are the key ideas, key requirement for the proof. So lemma. So this lemma says that suppose the first one is the following: if U comma V is in the Perron family, then their maximum is also in the Perron family. And so this is again easy to see because you already know that maximum of two subharmonic function is subharmonic, right? All you have to see is whether the boundary condition is valid. Both when we has the this boundary estimate, like lim sup of U and lim sup of V, each of them is bounded by some the same F. So maximum will also satisfy this condition. Okay, so this part is this is evident. Okay, so this part is evident. Something more interesting happens. Let me first draw a diagram here. So let's look at this domain D. And so consider a disk inside D. Okay. So Z0 and radius say R. We'll take maybe A. So suppose this disk, in fact, let's assume that the closure is actually inside D. And So let if so also let's start with one member in the Perron family. So define a new function. So I'm going to modify this member of the Perron family as follows. So define V to be. So you just take V to be Vz is equal to uz outside this, okay, z in d minus this dar. And what you do, see, you our definition of the subharmonic function is basically we take continuous functions, right? So I can look at the Poisson integral of u on the boundary of this disk. So inside the disk, I'm going to do the following. So I look at the Poisson integral, the PDAR of the boundary values of u. So this is if z is in the disk. So basically, this modification is only happening on this open disk, right? You are basically looking at the Poisson integral of the starting function u. Outside, it is the same function. You are modifying it to be the Poisson integral. So what this says that then V is still in the Perron family. Okay, and of course here you should also observe that this new function, this modified function, we usually call it Poisson modification. So this is always greater or equal to. So let me prove this part. The second part, the first part we have already seen. Let's call this one, maybe let's do. Again, this is not difficult. This part you can easily see, right? Because you see outside the domain, here so V is equal to U. And here V is equal to Poisson integral. So this disk, there's not an, so let's denote, let's call it D naught. So this is the Poisson integral of U. So you are extending U harmonically inside. So on the boundary of this disk, V is same as U, and V is harmonic inside. The maximum principle says that V will dominate U inside us, right? So by maximum principle, V is, greater or equal to U in the AR. Outside, V is equal to U. So V is greater or equal to U everywhere in the. So this is, so the modification is always at least as big as the original function. Now, how do I see the other part? So why is this? So I have to see that it is subharmonic. So first, let's see that it is continuous. And that is again, you see, outside the V is U, that is continuous. Inside the disk, because V is harmonic, that is continuous. But you have extended V as a harmonic function inside from the boundary, right? But up to the boundary of the disk, it is U. And then you are extending harmonically, means at least you are extending continuously also. So this means the continuity is never lost. Okay, so V is continuous on the, that part is evident because the continuity is never lost. Why does it satisfy the sub-mean value property? That is the only thing we have to check. But again, you see, if you take a point outside, I'll only show by picture. So if I take a point here, then V is just U. You already satisfy sub-mean value property. So sub-mean value property holds here, outside this closed disk. Yeah, that's an open set. So here, if you take any point, the sub-mean value property holds. If you take again inside the disk, inside the open disk, there also sub-mean value, because V is now harmonic, sub-mean value property will hold. In fact, mean value property. So a little bit of problem might, it looks like that you have some problem on the boundary, because if you try to show sub-mean value property here, so basically you have a circle now. which goes both outside and inside the yellow disk. But it's not a big deal because, so let's call this point as Z0. Then, so V at Z0, I want to show that the sub-mean value property holds here, right? So let's actually start with, no, it's fine. So V at Z0 is on the boundary of the disk also, V is U. U satisfy the sub-mean value property. Right? I want a V here, but that is, we have already seen that V is more than U, right? V is not, the modification is always bigger than U. So I can immediately replace this by, so this is not a big deal actually. This is also immediate. So I can replace U by V, preserving the inequality. So sub-mean value property also holds at the boundary points of the disk. So it holds everywhere. So V is subharmonic. So V is actually this rate argument actually shows it is actually valid for all Z, not just on. So this is true for because we have already established V is greater or equal to U. This line of argument applies to Z0 in ED. No. So you have to be no. Sorry, yeah, I'm using the equality. So this can be applied only on the boundary circle. So outside you have to use the fact that V is equal to U. Sorry, it holds outside. And on the boundary circle, inside V is 4. Okay, there you have to use the harmonicity. Fine. Okay, so this is the key lemma to prove that the Perron solution is harmonic. Since we are almost time, maybe it's a good point to stop here. Okay, I'll stop here. So if you have any question, please ask.
Sir, I have few questions.
Yeah, sure.
Sir, in your slide number 6.
6, okay.
Sir, when Z approaches to the boundary, how Vz goes to 0, sir?
Okay. This part, right?
Yes.
You see, I'm looking at maximum of U and 0. U, all possible limits of U are less equal to 0, right? So lim sup of U are less equal to 0 on the boundary, right? So you can never, so this part, the 0 part will dominate you near the boundary because all possible limits of U are, not more than 0. But here is this part which is already going to 0. So the maximum will go to 0.
Maximum will go to 0. Okay, sir. And sir, in your last slide, sir. Sir, you say that by maximum principle, V is greater than equal to U in DAR.
Yes.
So, sir, can you explain this part, sir? Why this V?
Yes. Yeah. So what is V here? V is C on the, so in the yield disk, you are defining it to be the Poisson integral of U on the boundary.
Yes.
U on the boundary. So on the boundary, this part, V is equal to U, right?
Yes, sir.
So V is a harmonic function inside the disk because it is Poisson integral.
Poisson integral.
And it is equal to U on the boundary.
On the boundary, yeah.
Maximum principle says that if you have a harmonic function that dominates a subharmonic function on the boundary, so equality means I can also write greater or equal to, right? V is equal to U means V also dominates U. Okay. So this is a harmonic function dominating a subharmonic function on the boundary. So inside the disk,
okay, sir.
It will be true.
Okay. Yeah.
Any other questions? Okay. If there are no questions, let us all thank Professor Borah for this very wonderful talk today. And we have the last fourth talk tomorrow at 3 p.m. and the Zoom link will be same.
Okay.
Yeah.
Yeah. Thank you so much. Yeah.
Thank you. Thanks a lot.